回11回これで OK かな。11回これでよいしょ。Okay, so I want to start today. So I'm at Koga Sensei. Then I have compass page here and blue cat page. This is 11th time of Susskind Quantum Mechanics. So the book is this one, Susskind Quantum Mechanics. Then I have a textbook here, Giga file, so you can download. Okay, then today we start from page 311. So page 311 is more like 31, I guess. So. Well, more. Okay, I think I finished path integral. So now we can move on to the next chapter, harmonic oscillator. Okay, by the way, let's see. This was. By the way, I have. Let's see. Let's click Susskind. I have questionnaire. I don't know, I cannot pronounce. Questionnaire or whatever. Survey. So you can click which time slot you like for the next time. 1 o'clock, 4 o'clock. No. 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, or 9 o'clock. Tomorrow, 9 o'clock. Maybe I can increase. I can increase this. Let me see. Or let me do this next time. Okay, anyway, so we can put this way. How do I do this? Tuesday, 10 o'clock. 10 o'clock or 3月8 Tuesday 11 o'clock or 3月8 Tuesday 1 o'clock or 3月8 Tuesday 2 o'clock. Okay, so I can put more maybe. 3月8 Tuesday 3 o'clock 3月8 Tuesday 4 o'clock I can do 3月8 Tuesday 5 o'clock. Okay, then I can do 3月8 Tuesday 9 o'clock. Okay, so please choose one of these. You can go to you can search hashtag SusskindQM. You can go to this Twitter survey. Yeah, I think so. You go to the newest. So then you show this thread. Okay. So today Monday, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, then 9 o'clock, tomorrow morning, 9 o'clock, 10 o'clock, 11 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 9 o'clock. So please choose. Okay, so let's come back to this harmonic oscillator. Art is Einstein. I think I see Lenny. The whole picture is slowly coming into focus. -1. General uncertainty. Entangled pair, the Hamiltonian, even the degenerate. What's next? Did we do degenerate? Anyway. Lenny is Bohr. Oscillations, art. Vibrations. You are fiddler. Fiddler.なんだこれ。これね。バイオリニスト。ペテンシ、バイオリニスト。You are a fiddler. Play us a last tune tonight. Something with good vibes. よかった。今日の、この会話はそんなに意味不明でもない感じ。あまりジョークになってないと思うけど。All of the ingredients that go into building a quantum description of world, of all the ingredients that go into building a quantum description of the world, to stand out as especially fundamental. The spin or qubit, of course, is one of them. In classical logic, everything can be built out of yes-no questions. Similarly, in quantum mechanics, every logical question boils down to a question about qubit. We spent a lot of time in earlier lectures learning about qubit. In this lecture, we will learn about the second basic ingredient of quantum mechanics, the harmonic oscillator. The harmonic oscillator isn't a particular object like a hydrogen atom or a quark. It's really a mathematical framework for understanding a huge number of phenomena. This concept of the harmonic oscillator also exists in classical physics, but it really comes to the fore in quantum theory. 前面4 comes to the fore 前 One example of a harmonic oscillator is a particle moving under a linear restoring force. For example, the ionic weight on the end of spring. Ionic 何ですか。象徴的な weight on the end of the spring. An idealized spring satisfies Hooke's law. The force on the displaced mass is proportional to the distance it has been displaced. We call the force a restoring force because it pulls the mass back towards the equilibrium position. Another example is a marble rolling back and forth at the bottom of a ball with no energy being lost to friction. What characterizes these systems is a potential energy function that looks like a parabola. V of x is k over 2 times x squared. The constant k is called the spring constant. If we recall that the force on an object is minus the gradient of v, we find that the force on the object is F equal minus kx. The negative sign tells us that force acts opposite to the displacement and pull the mass back toward the origin. Why are harmonic oscillators so prevalent in physics? Prevalent 流行している prevalent in physics because almost any smooth function looks like a parabola. Almost any smooth function looks like a parabola close to a minimum of the function. Indeed, many kinds of systems are characterized by an energy function that can be approximated by a quadratic function of some variable representing a displacement from equilibrium. Quadratic. This is 二次関数 when disturbed, these systems will all oscillate about the equilibrium point. Here are some other examples. An atom situated in a crystal lattice. If the atom is placed slightly from its equilibrium position, it gets pushed back with approximately linear restoring force. This motion is three-dimensional and really consists of three independent oscillations. The electric current in a circuit of low resistance often oscillates with a characteristic frequency. The mathematics of circuits is identical to the mathematics of masses attached to springs. Waves. If the surface of a pond is disturbed, it sends out waves. Someone watching at a particular location will see the surface oscillate as the wave passes by. This motion can be described as simple harmonic motion. The same goes for sound waves. Electromagnetic waves. Just like any other wave, a light wave or radio wave oscillates when it passes you. The same mathematics that describes the oscillating particle also applies to electromagnetic waves. The list goes on and on, but the math is always the same. Just to have an example in mind, let's picture the oscillator as a weight hanging from a spring. Needless to say, we hardly need quantum mechanics to describe an ordinary weight. And spring, so let's imagine a very tiny version of this same system and then quantize it. The classical description. Let's use y to denote the height of the hanging weight. We will choose the origin so that the weight is at y equals 0 when it's in equilibrium. That is when the weight is hanging at rest. To study this system classically, we can use the Lagrangian method that we learned about in Volume 1. The kinetic and potential energies are 1/2 my dot square and 1/2 ky square respectively. As you recall, the Lagrangian is the kinetic energy minus the potential energy. L equal 1/2 my dot square minus 1/2 ky square. First, we will put the Lagrangian into a certain standard form by changing from y to another variable that we will call x. This coordinate is not something new. It still represents the displacement of the mass, by switching from y to x, we are just making a convenient change of units. Let's define the new variable as x equals square root m times y. In terms of x, the Lagrangian becomes L equal 1/2 x dot square minus 1/2 omega square x square. The constant omega is defined as omega equals square root k over m and happens to be the frequency of the oscillator. By making this change of variables, we can describe every oscillator in exactly the same form. By making this change of variables, we can describe every oscillator in exactly the same form. In this form, oscillators are distinguished from each other only by their frequency omega. Now let's use Lagrange equations, Euler-Lagrange equations, to work out the equation of motion. For this one-dimensional system, there is only one Lagrange equation, Euler-Lagrange equation, namely this. Okay, the way I remember is ddt del L del x dot minus del L del x equals 0. This is Euler-Lagrange equation. So this becomes this. Carrying out these operations on equation 10.3. What is 10.3? 10.3. So we just plug in equation 10.3 to this. We put this one to this, here and here. We find del L del x dot equal x dot. Shall we try this? Okay, let me try. We have Lagrangian, which is 1/2 x dot square minus 1/2 omega square x square. Okay, so then we can calculate del L del x dot. This is x dot. We can also calculate del L del x. This is minus omega square x. So d dt del L. Okay. I think this book just shows this one. Okay, del L del x dot is x dot. This is called canonical momentum. This is canonical momentum. Definition. This one. This is the definition of canonical momentum. Canonical momentum P is defined to be del x dot. So the canonical momentum, in simple case, this is just momentum. Just the same momentum as Newtonian mechanics. Canonical momentum conjugate to x. Differentiating with respect to time gives ddt of x dot is x dot dot. And now we have the right hand side of equation 10.4. Left hand side, I think. This has to be left. Left hand side in equation 10.4. Turning to the now we have the so this is right hand side. So now we turn to the left hand side, then we find partial L partial x is minus omega square x. Setting the left and right sides, equations 10.7 and 10.6 of the Lagrangian equation equal to each other, we get minus omega square x equal x dot dot. This equation is, of course, equivalent to F equal ma. Why is there a minus sign? Because the force is restoring force. Its direction is opposite to the direction of the displacement. By now, you have seen this type of equation enough to know that the solution contains sine and cosines. The general solutions is x equal a cosine omega t plus b sine omega t, which shows us that omega is indeed the frequency of the oscillator. When we differentiate twice, we pull out a factor of omega squared. Exercise 10.1, find the second time derivative of x in equation 10.9 and thereby show that it solves equation 10.8. Okay, so we just do x dot. X dot is minus omega a sine omega t plus omega b cosine omega t. Okay, so then we take derivative again. Then we will see minus omega square a cosine omega t minus omega square b sine omega t. So this is minus omega square x. So this is just like this one. Minus omega square x equal x dot dot. Section 10.2, the quantum mechanical description. Now, let's return to a microscopic version of the weight and spring system. Let's say no bigger than a simple single molecule. At first, this seems ridiculous. How could we ever build a spring that small? But in fact, nature provides all sorts of microscopic springs. Many molecules consist of two atoms, for example, a heavy atom and light one. There are forces holding the molecule in equilibrium with the atoms separated by a certain distance. When the light atom is displaced, it will be attracted back to equilibrium location. When the light atom is displaced. The molecule is a miniature version of the weight and spring system, but is so small that we have to use quantum mechanics to understand it. Having worked out the classical Lagrangian, let's try to build a quantum mechanical description of our system. The first thing we need is a space of states. As we've seen, the state of a particle moving on a line is represented by a wave function psi x. There are many possible system states. And each one is represented by a different wave function. A function psi x is defined in such a way that psi star x psi x is the probability density, the probability per unit interval to find the particle at position x. Psi star x psi x equal px. In this equation, px represents the probability density. We now have a sort of kinematics, a specification of what the system states are. A specification of what the system states are. Kinematics is a specification of what the system states are. Kinematics. まあいいか。Kinematics. Kinematics 意味、運動学